Going. So, hi everyone. If you don't know me, I'm Nils. I've been GSIing for the course for the last month and a bit. Jesse's out of town today, so I'll be taking over the lecture today. Feel free to let me know if I need to change anything to help you guys get through this, and hopefully it'll go okay. All right. So, if you can remember all the way back to last week, we're talking about weighted least squares at the end of the lecture. So the weighted least squares problem is trying to find a vector alpha hat that minimizes, oh boy, that got all screwed up. Let me quickly fix this. Sorry for the handwriting. You can go back to the last week's notes too. So we're trying to find an alpha hat that minimizes the distance from A alpha hat to B under some norm given by a positive semi-definite matrix M. So to solve this, we construct the set of normal equations that we did before. So we project alpha into the space of M and A, or sorry, into the space of A. Using the normal equations, and then we can invert that matrix A transpose MA to give us our least squares minimizer. So this is a pretty general tool. It applies to a lot of things, and we'll see some of that in the homework. And today we're going to look at another application of this tool to the recursive least squares problem. So the recursive least squares problem as a general picture is trying to estimate a static value from a stream of data that has some noise in it. So we're going to write out the general expression for this. So our model is given by this equation. So here, yi is the data of the model. X is the value that we're trying to estimate. Ci is how that value x is translated into our data. And ei are a set of error terms that we have no knowledge of. So we know what Ci is. We are measuring yi. We don't know ei, and we're trying to find x. So here, Ci is an m by n matrix, sorry. I is the time index. Oh. Uh-oh. Well, that's a problem. Okay, so the tablet's freezing, which is great. Not sure why this is happening. Okay. So, a great start to a guest lecture, having equipment malfunction. So, I'm going to continue on the board if this is not going to cooperate, because that's not going to work. Okay, so we're gonna translate to the board. I'll post the notes after. I'll have them. It's mostly working off the handout that I gave out, so you should have something in front of you that's close. Okay, so I'm going to turn this off. Okay, so can you all see the board, hear the board? Good. So remember our model. Let's see if I can find a better one. Is given by Ci, or And there's no erasers. Or not 1 to n, it's just, it keeps going. Okay, again, Ci is a matrix, so x can be a vector, y can be a vector of a different size. So Ci is in R m by n. I is the time index. X is an unknown constant. So we get a better one. Yi are the measurements that we're making. And EI is our model error or model mismatch. That's a good question. There, better? Yeah. Cool, thanks. Okay, so again, we're getting data in yi. We're trying to estimate x, and it's being transformed by some matrix C that we know. So our goal is to compute a least squared estimate of x at a given time k using all available data at that time k. So let's say at time k, we have y1 all the way up to yk. Find xk hat, which is the argmin over x of the sum of all of our errors. We'll say yi minus cix transpose si times yi minus cix. So si is a weighting matrix of our least squares problem, and this weighting value can change at every step. So we also have an si data, and these are the weights of the data. Okay, so that's our goal, is to find this minimizer at every step k. So we can make this a little bit more concrete, and I'm going to walk through an example here to make it a little easier to see what's going on. So the example we're going to use is a kitchen scale. So you can imagine we have a scale sitting on our counter. Excuse my terrible drawing. So we have a scale, and we're trying to measure some object that has weight x, let's say. Now, coming out of that scale, we're going to have a stream of data, and this is going to be our yi. So every millisecond, let's say, our load cell is giving us some reading. Now, this is going into our RLS estimator. And this RLS estimator at every time is going to give us an xk. Or sorry, it's going to give us an xi. And that's going to go to whatever display is going to be in our scale. So picture it, if you've ever used a kitchen scale before, you put an object on, the numbers kind of change around for a little bit, and then they go to some fixed number. That's what we're doing here. So at every time at every time k, we're taking all of the past data that we had, from time 1 all the way to time k, and trying to find our best fit estimate as a least squares problem. So here, to kind of give some of these values some meaning here, we know our yi's are the measured weights. So the matrix C here is just going to be 1, because our measured weight should be a factor of 1 times our weight. So CI is equal to 1 for this example. Then our model error is going to be yi minus x. Then our data weights, we're going to actually call our data weights, we're going to set them equal to I over time. So the data weight increases as the time increases. Does anyone know why we might want to do that?
Because what you measured 10 minutes ago may not be necessary.
Yeah, so we want to discount stuff that we measured in the past. So probably that weight might have changed over time. We care more about more recent values. So this is kind of a discount factor that discounts values from before. Okay, so this is going to be something that we're going to come back to as the class goes on to kind of make what we do a little bit more concrete. So how do we go about solving this problem? Well, we can transform this into a problem that we've seen before. So remember the recursive least squares, the weighted least squares formulation that we had up earlier. This problem looks pretty similar to that, right? Except for this nasty sum here. So let's change our variables around so that that sum goes away. So we can kind of put everything into big vectors and matrices, and then treat this all as one big matrix multiplication. So to do that, we're going to define some matrices here. We'll say yk is going to be y1 all the way to yk lumped into a matrix. We're going to call ak c1 all the way to ck. Again, ek is going to concatenate all the errors. And then finally, we're going to concatenate all our weights, and we're going to put those into a matrix called rk. And instead of just putting them all down, because we're multiplying it from both sides, we're going to turn it into a diagonal matrix. So we're going to do s1, sk with zeros off the diagonals. Now you'll note that since each of the si's are positive semi-definite, gotta love going back, adding more assumptions. So each of the si's are positive semi-definite. So if we put them all along the diagonal, we end up with also a positive semi-definite matrix. A positive definite matrix, not positive semi-definite. Oh, shoot. So for the weighted least squares, we want a positive definite matrix. Okay. So when we do this, what happens if we take the value ak times yk? Well, c1 is going to multiply by y1 all the way down to ck multiplying yk. Sorry, if we multiply x by ak, not y. So this lets us write out our original expression, yi is equal to cix plus ei, as yi is equal to akx plus ek. So x is just going to multiply each ci to give you a yi over time. So then we can rewrite this as xk hat is equal to argmin of the sum, this is the ei times si times ei. So this is going to be equivalent to ek transpose rk times ek. Or if you wanted to write out EK using this formula, we end up with this expression. So this is the same problem that we had in the weighted least squares case. So we can actually just get the solution from this from that example. You okay if I erase some of this? This is all in the handout as well. So I'm going to keep working in the middle here. Oh, thanks. All right, so we had something that looked like our least squares problem. We can actually directly write out what the minimizer is of that least squares problem. So we know that xk the minimizing xk must satisfy the normal equations that we had written up first. And those are ak transpose rk times ak, xk hat are equal to ak transpose rk times yk. Sorry. And then since we know that this matrix is invertible, we can just invert that matrix to give us xk, right? Okay. Let's see what this looks like in the context of that problem and see if we can find an issue with this. So here are our yk is going to be y1 all the way to yk. Our ak is going to be all of the c's concatenated. Remember, the c's were just 1 in this case, so it's just going to be a vector of 1s. The rk, so remember our weights were increasing. And we're going to diagonally concatenate the weights, so it's going to be 1, 2, all the way to k, with zeros off the diagonals. Now we can write out this expression. So if we do ak transpose times rk times ak, you can actually do that pretty quickly. We know that ak, or we can compute that as just the sum of the numbers I. So if you take the 1 vector, multiply it by this number, you'll end up with a vector that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Times it by the 1 vector again, and you end up with the sum over all numbers. Let's say 1 plus 2. Okay, then the next vector we want to calculate is ak transpose rk. And this is just a vector 1, 2, k. So we can get our least squares minimizing solution. So AK transpose RK AK, inverse, so times sorry about that. It's just going to be the sum y1 plus 2y2 kyk over 1 plus 2 plus k. Okay, so kind of what you would expect to be the least squares minimizer here is you take the weighted average of all of the y's. So the most recent y's you multiply by a large number, and you divide by the sum of the weights. Now, let's say we wanted to compute this in real time. The yi's are coming out at, let's say, a kilohertz. So they're coming out once every millisecond. After 1 second, you now have 1,000 yi's that you have to add together in order to compute your estimate. Now this is still okay. After an hour, how many yi's do you have? You have a huge number of yi's. And this sum keeps getting bigger and bigger and bigger until eventually it becomes kind of infeasible to compute. So let's see if we can find a less uncomfortable xk to calculate computationally. We're going to actually just walk through computing it for a stream of vectors, and hopefully we'll see a pattern. So let's say yi's say it's like 10, 11, 9, 13. Okay, so x1 is just going to be 10 times 1 divided by 1. x2 is going to be 10 plus 2 times 11 over 1 plus 2. So that's 10 plus 22 over 3. x3 is 10 plus 2 times 11 plus 3 times 9 over 1 plus 2 plus 3. And you kind of get the picture. So you probably can't see that all that well. Apologize for my small writing. But what you should be able to see is that the sum from the previous term here factors into the next term. The sum from x2 factors into x3. So 10 plus 2 times 11 shows up down here as well. So we should be able to reuse these sums in some way when we're calculating xk hat. So I'm going to actually pose a challenge to you all. And that's to come up with an expression for xk hat as some function, or xk plus 1 hat, as some function of xk, yk plus 1, and the number k. So I'm going to give you a minute to think about this, and then you're going to talk to each other. So talk to your partners for a minute about how this might look, and then we'll see if you can come up with something in the meantime. Sorry to get you engaged this early in the morning, but figure this way you might not fall asleep so easily.
Oh, right. Yeah, you're right. It's just this. It's just something likely as the k by events in the case. So the first term we just have 10 times 1 equals 1. Second term we have 10 times 1 plus 2 times 11 equals 1 plus 2.
Okay. Yeah. But then what about the xk?
Yeah.
can write it in terms of x and y.
Oh, I see what you're saying. So then it would just be plus again.
Yeah, so you only really need to take the last yk plus 1. So you just add xk hat to the last yk plus 1 and then divide by sum of k and c stuff there.
All right. So coming back here, anyone come up with an answer they'd want to share with the class? I definitely heard the answer floating around in here, so I think a lot of you do know it. If none of you want to speak up, that's okay too. So you probably, or maybe you came up with something that looks along the lines of, where'd my marker go? So if you look, if you take x3 hat, you multiply it by this sum, and if you take x2 hat, you multiply it by this sum, add 3 times 9, and divide by the new sum, you end up with x3 hat. So we can express that as xk plus 1 hat is equal to xk hat times the sum from I equals 1 to k, I. Then we add in our term, which is k plus 1 times yk plus 1, and we divide by our new sum, which is sum from I equals 1 to k plus 1 of I. Sorry. My handwriting gets exponentially worse as I get down the board. Okay, again, probably hard to read there. The eraser's not working all that well. So we can actually rewrite this in the following way. So if we factor out an xk out of this expression, you'll end up with something like this. No, that's not quite right, sorry. Where'd that go? Oh yeah, no, that is right. That's correct. So if we take the sum of xk from I equals 1 to k plus 1, we minus xk plus 1. Yeah, no, this is correct. So sorry about that. So what you can see here is you take our old value of xk hat, then we add to it a difference between our current weighted estimate wait, no, that isn't correct. Shoot. Sorry, I had this on the computer. That's the expression that's correct here. Okay, so what we're doing here in this expression is we're taking the difference from our new value to our old estimate, multiplying it by some gain, and adding it to our old estimate. Some terminology here. This is going to be called your Kalman gain in the recursive least squares filter. And when we move into more dynamical systems, this is going to be something that plays into the Kalman filter, which is maybe something that you've heard of before. These are your updates, and this is kind of the modeling error at each time step. So this is in the specific case of the scale. We've come up with a way of computing our new value at every time, and we only have to use our old value and then inverting this sum, which again is maybe not the nicest sum to invert, but you can also express this sum recursively as the old version of this sum plus a new one. So we're gonna write out what this looks like in the more general case, and this is gonna build our recursive least squares filter. Okay, so again, the problem that we were facing earlier is that this matrix AK grows to be a k times m or m by n matrix. So it ends up being a really large matrix. And then we have to multiply it twice or 3 times. We have to invert the product of that. It ends up being a computationally complex solution, like we saw. So let's express the normal equations at time k in some form. So this is moving back. So remember, we converted from a sum to a matrix multiplication. Now we're converting back from that matrix multiplication here to here. Again, this is just following through your handout if you're looking for the actual text. So we're going to define this matrix, this sum as mk. Then we have that mk plus 1 is equal to mk plus our new term in the sum. Okay, so we can compute this matrix now recursively. So before this was a really big matrix compute. Now all we need to do is at each time add our new weight matrix times our new transformation matrix. So we can rewrite now our normal equations in terms of mk plus 1. I'm going to go back and erase this now. So we can rewrite our normal equation there as mk plus 1. Oh, geez. And we can break up this sum from I equals 1 to k plus 1 as I equals 1 to k plus the k plus 1th term. So c k plus 1 transpose s k plus 1 times y k plus 1. So we note that from our last time step, this is equivalent to mk times xk. So remember, mk times xk was equal to this sum, which is appearing again over here. So we can express that as mk times xk hat plus ck plus 1 transpose sk plus 1 yk plus 1. So this is starting to look like a recursive solution where everything is only expressed in terms of the k plus 1 term and the kth term. And there's the only new information that's happening is this update where mk plus 1 is just adding that matrix here, and this expression is adding that matrix here. So this gives us a recursive solution for xk plus 1, and that's equal to mk plus 1 inverse times mk xk hat plus ck plus 1 transpose sk plus 1 yk plus 1. But we also know from over there that mk k plus 1, or sorry, mk is equal to mk plus 1 minus ck plus 1 transpose sk plus 1 yk plus, or ck plus 1, just from our expression down here. And so if we sub that in for mk, we end up with xk plus 1 hat is equal to mk inverse times mk plus 1 times xk, so that's xk hat, plus mk plus 1 inverse times ck plus 1 transpose sk plus 1 all times yk plus 1 minus ck plus 1 times xk hat. Okay, this is a lot to digest. I know I'm feeling it as I write it down. But again, if we look here and we look back at the solution we came up with over here, it looks pretty similar. So we have their old value. We are adding a term that's the difference between our new value minus our old value. And we're multiplying it by some updated gain matrix. So at every time step, we're computing mk plus 1, and then we're computing xk plus 1 from our old value of xk, our difference to our new measurement, and that mk plus 1 inverse term. So we call this the Kalman gain, and we call these innovations. So this is great. We now have a recursive solution. So this is a much easier solution to compute than what we were doing before. Now there's still a problem here. So mk plus 1, which is kind of this matrix plus which is going to be the size of that matrix, has a size of so ck can be pretty large. I think that's the idea here. So in practice, mk plus 1 can actually be quite large. So in our case of the scale, it was just one-dimensional. But if yi is now a big set of vectors, this can be a really large matrix. So we're going to actually do an alternative to this that uses the matrix inversion lemma in order to reduce the computational complexity even further in the case that MK is a large matrix. So we don't want to have to invert a large matrix every time we compute a new update. So I'm going to erase this example because I think it's given up its use. And I'm going to erase this. Okay, so we're going to use something that we've seen before, and it's called the matrix inversion lemma. And it's a way of computing the inversion of a sum of matrices by inverting its components. So the matrix inversion lemma states that if you take the inverse of A plus B, C, D, and it's going to be A inverse minus A inverse B, this horrible mess of algebra. So this looks like it's a much harder thing to compute than that, but depending on the sizes of the matrices A, B, C, and D, and the form of the matrices A, B, C, and D, this might be an easier thing to compute. So we're going to do a substitution to this lemma. We're going to say that A is MK, B is CK plus 1 transpose, C is SK plus 1, D is CK plus 1. So this gives us an expression for MK plus 1 inverse. So remember MK plus 1 was equal to MK plus CK plus 1 transpose, SK plus 1 CK. So if we want to find MK plus 1 inverse, we can use the matrix inversion lemma. So and again, a horrible mess of algebra. But look, the only times we need to use MK inverse, the only inversions of M that we're making are inversions of MK. So if we keep computing this recursively, we don't need to keep computing MK at every time step. So let's define PK is equal to our MK inverse. Then we have an update for PK, which is PK plus 1 is equal to PK minus, again, this horrible mess of algebra, and I'm going to write on the board just to drive it home. So it's going to be an update that only needs to invert C times P times CK plus 1, which is a smaller matrix than M is. So finally, if we take that expression for PK, we end up with an update for XK plus 1 hat. That only depends on PK. Okay, so this is going to be our recursive formulation for the least squares problem that computes the recursive least square, or that computes the least squares estimator in a much more computationally attractive fashion than that batch solution that we computed earlier. It's a mess of algebra, but when it comes down to it, intuitively what we're doing is taking the old measurement, finding the difference between, or say our old estimate, finding the difference between our old estimate and our new measurement, and multiplying it by some update matrix that's also computed recursively here. And you can think of this as a gain on the estimator, this is the error of the estimator, and this is the previous value of the estimator. So that's all we're gonna cover for today. What's up?
I don't really understand how we're saving computation on computing MK inverse. Because we just made a substitution, but if we're like computing this, you would still have to compute MK inverse, right?
So you would compute M1 inverse, right? Once.
Okay.
So you'd compute, and then M2 inverse, we can find as a function of M1
Oh, okay.
or of P1. And we never have to invert MK again. So we only have to do it one time rather than every time step. And if you think about the computations that are happening every time step, they're happening every millisecond. That's something that we really want to make as light as possible. Cool. So thanks for coming in. I'll be up front for a bit if you have any questions.